Hey everyone, and welcome to this explainer. Today, we're tearing into the essential physical properties of solid waste. You might think it's just a bunch of everyday trash, but understanding these exact physical characteristics is absolutely what dictates modern environmental engineering. So let's dive right in and see how a simple garbage bag is actually a highly complex system of variables that engineers have to master. Here's our roadmap for today. We're covering 6 quick modules: the blueprint of waste, composition and particle size, density and compaction, moisture dynamics, energy recovery potential, and finally, system design. All right, Section 1, the blueprint of waste. Why do we even bother analyzing the trash so closely? Well, the crucial takeaway here is that understanding the physical properties of waste is literally the bedrock for designing functional disposal systems and figuring out what equipment we need. Think about it. You just can't build a multi-million-dollar sanitary landfill or buy a massive fleet of collection vehicles without a rigorous blueprint of what you're actually dealing with. The data absolutely has to drive the design. Moving to Section 2, composition and particle size. What exactly is sitting inside that municipal solid waste stream? Just look at this typical breakdown. It's kind of wild, right? Paper actually dominates at 34%, followed by organics like food waste at 14% and garden trimmings at 12%. So those 3 categories alone make up a huge chunk of our everyday waste. But honestly, composition is only half the story. Because beyond just what the waste is, the actual size of these particles is a completely vital metric. Particle size distribution varies wildly. You go from a tiny scrap of cardboard to a massive broken appliance. And why does this matter? Well, if you're engineering mechanical separators to sort recyclables or designing industrial shredders to break down volume, those machines must be calibrated for specific particle sizes. Get the math wrong here, and your entire processing line will just constantly jam or break down. Okay, Section 3, density and compaction. This is a metric that totally changes the game economically. So density is simply defined as the mass of waste per unit volume, usually measured in kilograms per cubic meter. And the reason this is so critical is that density dictates pretty much everything, from the total size and lifespan of a sanitary landfill down to the exact type of collection trucks a city has to buy. It's basically the ultimate measure of spatial efficiency. And you see a dramatic difference the second engineering is applied. Uncompacted waste usually sits around 100 kilograms per cubic meter, but if we use normal compaction equipment, we can achieve a massive 75% reduction in volume. That rockets the density all the way up to an impressive 400 kilograms per cubic meter. To put that into real-world perspective, this means a single collection vehicle instantly becomes 4 times as efficient, entirely through the mechanics of applied pressure. Instead of sending out 4 open-bed trucks to collect a neighborhood's trash, you only need 1 single compaction truck. That is a staggering savings when you factor in fuel, labor, and maintenance. But keep in mind, density is definitely not a static number. Actually, scratch that, it's constantly shifting from the moment it leaves your curb to the moment it hits the landfill. Things like scavenging alter the composition, rain and sun cause wetting and drying, the actual vibration of the garbage truck shakes it down, and of course, natural decomposition is always breaking it apart. As an engineer, you're constantly aiming at a moving target. Section 4, moisture dynamics and leachate. Let's talk about water's incredibly complex role in our trash. Simply put, moisture content is just calculating how much of the garbage's total wet weight is literally just trapped water. When we toss out wet food scraps or damp yard trimmings, we're basically just throwing away water. To find out exactly how much water is hiding in there, we use a really straightforward equation. We take A, which is the initial mass of the wet sample, and we subtract B, which is the mass after it's been completely dried out. Then we just divide that difference by our initial mass, A, and multiply by 100 to get our percentage. Now, how do we get that dried mass? Well, in the lab, the sample is strictly dried in an oven at exactly 77 degrees Celsius for 24 hours. Why that specific temperature? Because it's hot enough to completely dehydrate the water, but low enough to stop us from accidentally vaporizing other volatile materials inside the waste, which would totally skew the data. Typically, this process reveals that standard municipal waste has a moisture range of around 20 to 40%. So why does all this water matter? Honestly, it's an economic nightmare. Moisture increases the total weight, which instantly spikes transport costs. You're essentially paying good money to truck water around. On top of that, it completely ruins the economics of incineration. If the waste is too wet, the facility wastes precious, expensive energy just boiling off that water before the trash can even catch fire. This is exactly why you'll see waste transfer stations heavily insulated from rainfall. Inside the landfill itself, engineers track something called field capacity. Think of it like a sponge. It's the maximum amount of moisture the waste can hold onto before gravity finally wins. Once the waste passes its field capacity, say after a massive rainstorm, gravity pulls that excess water straight down through the rotting garbage, creating highly toxic landfill leachate. And just like density, field capacity changes depending on how heavily compacted the waste is. The movement of that toxic leachate and dangerous landfill gases like methane is totally dictated by the waste's permeability. And permeability relies on porosity, which is just the amount of empty voids per unit volume. For solid waste, porosity usually ranges from 0.40 to 0.67. If an engineer doesn't calculate this accurately, that landfill could literally leak poison straight into the local groundwater. Section 5, Energy Recovery Potential. Let's pivot from burying trash to recovering the hidden value inside of it. Calorific value is the absolute golden metric here. It tells us exactly how much heat energy we can recover if we decide to burn the waste instead of throwing it in a hole. It's usually expressed in kilocalories per kilogram. To figure this out in the real world, we use a fascinating piece of lab equipment called a bomb calorimeter. We take a completely dry sample, place it inside a sealed vessel packed with oxygen, and ignite it. We then measure the exact heat output generated into a surrounding water jacket that's kept at a constant 25 degrees Celsius. This provides the hyper-precise data engineers need to design efficient waste-to-energy power plants. And finally, Section 6, Summary, System Design. We've covered a ton of ground, so let's tie it all together. Remember, these physical characteristics aren't just boring academic numbers sitting in a textbook. They are real-world constraints. So ask yourself, if a municipality miscalculates moisture content and density, how quickly will their transport budgets collapse and their landfills start leaking leachate? If you ignore the science, budgets collapse under the sheer weight of hauling trapped water, and poorly compacted landfills will inevitably fail. The next time you toss something in the bin, just think about the incredible chain of physics and engineering required to manage it all safely. Thanks so much for joining me for this explainer. Keep asking those big questions, and I'll catch you in the next one.